Do you have any questions from last time? I ended last time with that one example problem. We have a quiz at the end of class today, but until then I'm just going to do more examples with two-dimensional kinematics. Okay, so here's the first one. A ball's launched horizontally from a height of 1 meter. The speed at that instant is 20 meters per second.
I think she wants you to repeat it.
Keep your yap shut, Siri. No one's talking to you. How long does it take for the ball to hit the ground? So let's call that part A. And second, how far away horizontally does the ball hit the ground? Okay, so it looks something like this. This ball is launched out of a standard ball cannon. Yeah, right. But this one uses gunpowder for some reason. And we know that at the instant it's launched, the ball is going 20 meters per second horizontally. So at the instant it's launched, its velocity vector is horizontal with a magnitude of 20 meters per second. And then after that, it's going to follow a parabolic path. It's going to hit the ground somewhere out here. This distance is 1 meter. Okay, so the first thing we have to do is make those 4 choices. The instant for time equals 0, the instant for time final, the origin location, and the coordinate system axis orientation. For time equals 0, that's going to be the instant that it's launched. Time final is the instant it hits the ground. The origin location, this is a choice I'm going to make a lot of times. I'm going to put it on the ground beneath the launch point. And then the coordinate axes, we're always going to choose the y-axis up. And and that means the x-axis has to be horizontal because they're perpendicular. I'm going to always choose the x-axis in the direction of motion. So horizontal in the direction of motion. So if you draw that, the coordinate system is down here. There's the origin. There's X and Y. And now we're going to list what we know and what we want. And it's a lot longer process now because we have to go through 11 variables. Do we know time final? No, that's what we want. Do we know anything about the acceleration? Yeah, we know for free fall we always know everything about that. So AX is 0. AY is negative 9.81. Do we know anything about the initial position, the position when time is equal to 0? Yep, that's right. So what we're doing there is we're trying to figure out the coordinates of the object's location when time is equal to 0. So the coordinates are, it's just 1 meter in the positive y direction, no distance horizontally from the origin. So PIX is 0, PIY is positive 1 meter. Anybody have any questions about that? Do we know anything about P final? Y is 0. So we don't know. So P final X is going to tell us how far away it lands. We don't know that, but we know it's on the ground when we get to time final. And the ground is a y, a height of 0, a y position of 0. So PFY is equal to 0. We don't know PFX, and at least for part A, we don't care about that. And then what about the initial velocity? Do we know anything about that? So we know that the initial velocity vector looks like this. It's 20 meters per second horizontal. And if we put the tail at the coordinate system, this just becomes one of those vector problems. So what angle do you have to go from the positive x-axis to get to that vector? 0. So this is, this is 20 times the cosine of 0, 20 times the sine of 0, which just gives you 20, 0. You can also think of that as it's pointed in the positive x direction. So that entire length of 20 is in the positive x, as a positive x component. So for any of them that are just on these quadrant lines, on these quadrant axes, eventually, if you can't see it yet, you'll be able to just eyeball that. It's in the positive x direction, 20. And so based on this, we know that VIX is 20 and VIY is 0. And do we know anything about V final? No. So this is what we have. Is there an equation that'll give us time final? I think the one that'll work is, yep, and so P final Y is equal to P initial Y plus V initial Y times time final plus 1/2 AY T final squared. PFY was 0. PIY was 1. VIY is 0, so this whole term is 0. And then this gives minus 4.905 TF squared. So negative 1 is equal to, no, let's do it the other way. Positive 4.905 TF squared is equal to 1. And so TF squared is equal to 1 divided by 4.905. I don't know what that is. But then when you take the square root, you get TF is equal to plus or minus 0.452. And then you have to have a reason for choosing the positive or the negative. What's the reason here?
Time is not negative.
Right, we're never going to use negative times, so we're going to take the positive. Notice that this equation is exactly the equation we would have if this was motion along a line and you just held an object out 1 meter high and dropped it. You have the final position is the ground. The initial position is 1 meter. There's no initial velocity, just like you're dropping it. And then you have the acceleration of gravity. So that's telling the same story that video about the bullet and the bullet being dropped told. You can't tell any difference. So I should say the horizontal and vertical motions don't affect each other. So the fact that this has a horizontal velocity doesn't change how long it takes for the bullet to hit the ground. So this is the time that it would take to drop the ball to the ground, and it's also the time that it takes for the ball to hit the ground if you shoot it out horizontally. And then part B, now we're trying to figure out horizontally how far away the ball hits the ground. Those 4 things that we have to choose, those are all the same. There's no reason to change those. What we know and what we want. Well, we know all the old stuff. And we also know that time final is equal to 0.452 seconds. And this time what we want to find is PFX. So an equation that'll work with this says PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to, what's the X component of the initial position? That was the velocity. So this is 0. And then VIX is 20. So we have 20 times time final that we calculated before, 0.452. And then what's the X component of the acceleration? 0. So this whole term goes away. So 904. So this is 9.04, I think, meters. Any questions about that? So what if the, so think about the bullet and the, I mean, it's the same kind of example as this. Think about the bullet being shot and the bullet being dropped. And we saw that video that said they hit the ground at the same time. What if the bullet wasn't shot horizontally? What if it was shot at an angle up a little bit? Would they hit the ground at the same time then? Can you picture what in the equation would make that different? What would happen is the reason that the time here for launching this ball out to hit the ground is the same as it would be if you dropped it, is that there's no vertical component to the initial velocity vector. Okay, so VIY was equal to 0. And so that equation ends up being just like if you dropped it. But if you shot a bullet, even at a small, say you just shot a bullet 5 degrees above horizontal, you know, here's horizontal, and you shot it like this. Well, if the bullet's going 1,000 meters per second, the sine of 5 degrees is a small number, but when you multiply that by 1,000, you end up getting a pretty big VIY, a pretty big initial velocity. And so even a small angle up like that means the bullet would hit the ground a lot later than when you dropped. So for that thing to work, for a bullet being dropped and a bullet being shot to hit the ground at the same time, the gun has to be very carefully set at 0 degrees. Okay. Here's another one. So, I know you've all done this before. This is a popular game. So, you're on a unicycle. And you're holding a ball. Unicycle. Trying to remember what it. You'll be sure after this. Let's see. I'm trying to remember what a unicycle looks like.
That's pretty darn good.
Oh, well, thank you. Okay, so the unicycle is going this way at 5 meters per second. And you want to figure out, okay, and there's a cup on the floor over here. And the top of the cup is above the ground 0.15 meters. That's how tall the cup is. And you're going to release the ball from a height of 1 meter above the ground. And you want to know how far away from the cup do you need to release the ball so that it lands in the cup. Remember this game? Unicycle cup? So what's that distance? obviously you want the ball to land in the cup. You could imagine this on a ping pong table. Then it makes more sense. Okay, so any questions about the problem setup? So we have to choose those four things first. So time equals 0, time final, the origin location, and the coordinate system orientation. What do you want to choose as time equals 0?
The second he lets it go.
Yep. So the instant it's released. And what do you want to choose as time final? Yeah, and so what we're going to do is we're going to say time final is the instant that the ball gets to a height of 0.15 meters. The origin location, I'm going to choose the origin location and the coordinate system orientation the same way I did in the last problem. I'm going to put it on the ground, right beneath where the ball's released, so right beneath the ball when time is equal to 0. And I'm going to make the y-axis point up and the x-axis point horizontally in the direction of motion. So the origin is on the ground beneath the release point. And the coordinate system orientation has the y-axis up and the x-axis horizontal in the direction of motion. And now we're going to list out what we know and want. Do we know time final? No. If we can get by without it, that's fine. So I'll leave that off. Acceleration, this is a free fall problem, so AX is 0. AY is negative 9.81. Initial position. What's the X component of the initial position? 0. And what's the Y component? 1, yep. Do we know anything about P final? So we know that when we get to time final, the position is 0 because it's on the ground. So PFY is equal to 0. Do we know any questions about that? Oh, yes. Thank you. You're right. Any questions about that? So X we don't know. X is this. So we're trying to figure out how, yeah.
Can you say the question one more time?
What we're trying to figure out? We're trying to figure out when he releases the ball, how far away does the cup have to be horizontally so that the ball lands right in the cup? Okay, so that's what we're looking for, PFX. Do we know anything about the velocity? The initial velocity? Yeah, he's dropping it, so the initial velocity is whatever the velocity is of the vehicle or whatever he's dropping it from. So that's horizontal with a speed of 5 meters per second. So VIX is 5 meters per second, and VIY is 0. And this comes from the same thinking as before. The velocity vector is horizontal with a magnitude of 5 meters per second. If you put that tail of that vector at the origin of the coordinate system, then that vector is pointing in the positive x direction, so the whole thing is a positive x component. There's nothing in y. Or you can think of it as 5 times cosine and sine of 0 degrees. And then do we know anything about the final velocity? No. All right, so is there an equation that works with these? That's right. There's nothing that works, so we have to find T final. And for that one, I think the equation that's going to work is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So that says 0.15 is equal to 1 plus this term is 0 because VIY is 0 minus 4.905 TF squared and so subtract 1 from both sides, we get negative 0.85 is equal to negative 4.905 TF squared. And then divide both sides by 4.905. So negative 0.85 divided by negative 4.905 is equal to TF squared. So this ends up being positive, and then you can take the square root and you get 0.416 seconds is equal to time final. And since we took the square root, that can be positive or negative. This is a time, so we know that we have to take the positive one. Okay, so now that we know this, we can chalk this up as one more thing we know. And now we can look for an equation. Now that we have more information, hopefully we can find an equation that will give us what we're looking for. So now we can use PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 5 times 0.416 plus 0 because AX is equal to 0. And so PFX is equal to 2.081 meters. So if you mark off 2.081 meters from the cup, and you go exactly 5 meters per second and release the ball from exactly 1 meter high, it should go right into the cup. Any questions about that one? Okay, let me do one more, and then, well, maybe we'll have time for you to work on one after. Otherwise, we'll just have to wait till Tuesday, and I'll give you one to work on together. But let's say that you have a gun. That's what guns look like.
Did you go see Magnificent Seven?
No. And, oh, well, dang. I don't want it like that. Okay, I'm not going through that again. This is what the gun looks like now. So say you shoot a bullet into the air. Say that it leaves the gun at 1,000 meters per second. And let's say that you shoot it with an angle of 20 degrees above the horizontal. And let's say that this is the ground, just to make the calculations easy. Or it's the water. What? Yeah. This is water. So he's shooting it half underwater. So the bullet leaves from the height of the ground. How high is the bullet at its highest point? And second, when it reaches the highest point, how far has it traveled horizontally? All right, time equals 0 is the instant that it's shot. Time final is when it reaches the highest point. The origin location, I'm going to put at the ground, and the coordinate system orientation is going to be like that. So the origin location this time is at the location of the bullet when shot. And the coordinate system orientation has the y-axis up and the x-axis horizontal in the direction of motion. Okay, do we know time final?
No.
No. Do we want it? No, we can do without it.
No, because, no, we want time final for B.
Well, yeah, eventually we are going to need it. You're right about that. But for now, I'm just saying, like, if we can get by without solving for T final, we'd be just as happy. Acceleration, it's free fall, so AX is 0. AY is negative 9.81 meters per second squared. Initial position, what's PIX? Yep, 0. PIY? Also 0. Anybody have any questions about those? Do we know anything about PF? We want that for the second part. Let's just leave it off for now. So what we want is PFY, right, for the first part. And for the second part, we're going to want PFX. What about the initial velocity? Do we know anything about that? Yeah, we can get that. So we're going to get these from the fact that the initial velocity vector makes an angle of 20 degrees with the horizontal. And has a magnitude of 1,000 meters per second. So this initial velocity vector is 1,000 times the cosine of 20, 1,000 times the sine of 20, which is 940, 342. So VIX is 940 meters per second. VIY is 342 meters per second. Do we know anything about the final velocity? That's right. For this problem, we do need to specify that because we're looking for the highest point. So we know that we don't know anything about the x component of the final velocity. Well, it turns out in free fall problems that just stays the same through the whole thing, but we don't need to know that. The only thing we need to specify is that VFY is equal to 0. All right, is there an equation that'll work with these? I think probably this one will. 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So we get 2 times negative 9.81 times PFY minus 0 is equal to 0 squared minus VIY was 342, so 342 squared. So negative 19.62 times PFY is equal to negative 342 squared. What's 342 squared? 16964. 0.1? Oh, there's 116964. That's huge. That's gigantic. Okay, so now divide both sides by 19.62. And what do you get there?
Negative 5961.
5961.5. That's not right?
No, that's right.
Okay.
Is that negative?
It's not negative, right? The negatives cancel. And this is meters. Okay, so how far is that in miles? It's like 3 point something miles in the air. That's a lot. And so now for part B, those 4 things we have to choose, we'll keep those the same. The things we know are still going to be all the old stuff. And now we know that PFY is equal to 5961.5. And the thing that we want to find is PFX. So is there an equation that works with these and this and trying to find PFX? No, so we're going to have to find time final.
Could we also, since we know that acceleration is 0, go to VFX and just use the third equation? Actually, no, that doesn't work.
No, right. We still have 2 things we don't know.
Yeah, we'll take it back.
So find TF. Okay, so there are 2 equations we can use to find TF. Might as well use the easier one. So let's use VFY is equal to VIY plus AYTF. VFY is 0. VIY is 342. AY is negative 9.81. So negative 3, let me write it this way. So 9.81 TF is equal to 342. So TF is equal to 342 divided by 9.81. What do you get for that? What is it? 34.86. Holy moly. Seconds. I think bullets might not go this fast. I think that might be the issue we have. But, so that's not even before it hits the ground. That's just how long it takes to get to the highest point. So now we can use, now we also know this. And so we can use PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 940 times 342 plus 0. And so what do you get for PFX?
Would it be 940 times 34.86?
Yep, you're right. 34.86. So what do you get for PFX? 32,000 what? 68.4 meters. So 20 miles. The speed of sound. Anybody know anything about how fast bullets go? I think. Yeah. Way higher. This is way higher. So the speed of sound is like 342 meters per second. So this is, so I did this at 3 times the speed of sound. Is that possible? Are there? Yeah. Okay. Wow. Yeah. So 20 miles. But I have a question about this. So in our lab, our air resistance lab, what we saw was that when you're dealing with metal objects, whatever, and you're dealing with the kind of speeds that you would get from dropping it like 60 feet or whatever, for the metal objects, there was barely any difference, right? What do you think about this? Like, is this a reasonable, would we get good results with this free fall approximation here? No, because the speed is just so high. And as that speed goes up, you get a huge increase in air resistance. It goes up really steeply. So if something's going 1,000 meters per second, the air resistance is gigantic. And so, no, this would not give very good results. But that brings up another sort of like interesting question. When I showed that video, that was a bullet, you know, and the results of that experiment were exactly what the free fall approximation would tell you. So what's going on there? That's sort of a, how come this doesn't work at all, but this approach gave a perfect prediction of what was going to happen in that experiment? The answer is that, remember, the horizontal and vertical motions are independent of each other. And so air resistance was having a huge effect on the bullet's horizontal motion. But its vertical motion, it never had a very, very high vertical component of velocity. Its vertical velocity was just what it would be if you dropped it. And so air resistance had a huge horizontal effect on the motion, but a negligible vertical effect on the motion. Or in other words, the effect of the air resistance on the vertical motion was exactly the same as the effect of air resistance on the dropped bullet. Any questions about that? Okay, let's just take the quiz, and at the start of next time, I'll give you a problem that you can work on together. But now, we've covered all the material so that you can start looking at those two-dimensional kinematics practice problems. So start getting to those as soon as you can.